All right. Hi there, everybody. I'm back home now. I started this lecture 3 separate times over there at that hospital and got distracted each and every time by somebody coming in within the first 2 minutes, so I'm just starting it from scratch. Okay. So, what we have today is lecture 7, overview of statistical hypothesis testing. And so we're going to talk about the z-test. Okay. Now, the z-test is something that you basically know already. You know all the details of the z-test. We've been over it all before. We'll formalize it today. But what's really the new part here is this thing called hypothesis testing. And hypothesis testing is going to be a 4-step procedure. And this 4 steps that we're going to learn are going to be appropriate when we use a z-test or an independent t-test or a related t-test or an ANOVA or etc. A whole bunch of different statistics that will all rely on this same 4 steps of hypothesis testing. Okay? So let's start up with a couple of definitional terms here. First one being inferential statistic. Now, we know what happens. Remember we talked in lecture 1 or something. Scientists often want to know big questions. Like, what is the opinion of the American people of the president? And you're like, it's just too big of a question. There's too many American people. So you draw a sample of scores, right? You calculate descriptive statistics, means and standard deviations, and etc., on that sample. Then you use the information that you find in the sample to infer about what the population would be, right? Even though the population is an unknowable thing, we can make guesses or inferences. And so inferential statistics are basically situations where we have information about a sample, and we're going to use that information to make the best inference we have about what the population would look like if it was possible to actually see the entire population. So these inferential statistics are often referred to as hypothesis testing procedures, which is of course the name of this lecture, right? Hypothesis testing. So inferential statistics come in 2 different types, parametric and non-parametric. And so parametric inferential statistics are those that involve, well, just as some examples, the parametric ones are the z-test, the t-tests that we'll learn, the independent t, the related t, the ANOVA we're going to learn briefly. So parametric statistics are inferential procedures that are used if, back when you were doing descriptive statistics, if the mean was the appropriate measure of central tendency, then pretty much parametric statistics are appropriate. If the median or the mode was the appropriate measure of central tendency, then you'll probably be doing non-parametric statistics. And you guys kind of saw a little bit of these when we did that very first lab assignment, and you had the little chart, and it was like, if you have this many independent variables and this many levels and the scale of your dependent variable. And remember on that chart, some of the statistics on there, I mean, you didn't realize it at the time, but some of those on the top of the chart were called parametric statistics, those that use interval or ratio scale data, and those that use nominal or ordinal scale data are non-parametrics. And so the non-parametrics we do not touch in our class at all. We'll never get there. Just know that we are doing these parametrics, but there's a whole world of non-parametrics that exists on the opposite side. So, as we said, there's many kinds of hypothesis testing procedures. We're going to use the z-test. And yeah, look at that. The exact one you use depends on the situation you're in. And you guys are already familiar. Your situation. How many independent variables? How many levels? What's the scale of the dependent variable? Is it repeated measures? Is it between subjects or within subjects? I think that's what we call it. And so all of a sudden, it's just a matter of which one is appropriate. Okay. Yeah. It's sort of like, let's say, for example, yeah, we're going to do apparently an SAT class, okay? Now, let's imagine, and I mean, I looked it up this yesterday, I guess. The SAT has a mu of 1,000 and a sigma of 195. Okay, I have it written down on some other slide where it becomes relevant. But mu of 1,000, sigma of 195. And let's say, for example, I add an SAT class. Okay, what happens is I'm assuming that if my SAT class is effective, then the mu or mean or average of people that take the SAT after taking the class is higher than if they did not take the SAT class. Okay, and so we know in this case the population of raw scores. That is, on the SAT, mu is 1,000 with a sigma of 195. What we don't know is the population of scores of people that have taken this SAT class that take the SAT. Okay, so we have a mu of people that have not taken a class. We do not know a mu of people that have taken a class. Okay, and so that's kind of what we're working with here. So it's going to allow us to test questions, essentially, keeping it simple. We'll formulate it, but right up front, does the class that I have created really change people's scores on the SAT? Because that's really what it comes down to. I've got a population of SAT with mu of 1,000. I have created a class. I measure a sample. Do I believe that the sample that I have of students that have taken my class indicate that the class truly makes them better? Okay. This one I'm on. This one. So hypothesis testing involves a 4-step procedure, and we'll break apart these 4. First off, stating the hypotheses, and again, we're going to really give you some formal stuff here, but stating the hypotheses. Given this idea of an SAT class, the hypotheses are pretty straightforward. Either this new class for the SAT doesn't help people, or it does help people, right? It's pretty straightforward. These are going to be the hypotheses that we will formalize. We're going to need a set of criteria for decision. And again, this is something we have touched upon. We looked at I remember we looked at a alpha equals 0.05, 2 tails, and we had to look up the 0.025. So we've already touched on this notion of setting a criteria for a decision. I remember it was with that Fred and Ethel's bowling alley example the other day. Okay? Collecting sample data. Well, you're lucky. You're in stats class, and we collect the data for you. So step 3 doesn't even count. And then step 4 is evaluating the null hypothesis, which means we're going to have to calculate that z-test and then compare it to the critical areas that we set from step 2 there. Okay, so step 1, we create hypotheses. Step 2, we set up a criterion for making decisions about the hypotheses. Sample data is done for us, and then evaluating the hypotheses. So we're going to make decisions. Is the data I've received in the critical region or not? So now let's get some details on how this whole thing is going to work. Okay, step 1, stating the hypotheses. Number 1, there's always 2 hypotheses, always. They're called the null and the alternative. Okay, the null hypothesis means nothing. You see it's symbolized by H sub 0. That's not an H sub O, that's a 0. 0 meaning nada, nada, nothing. Okay, so the null hypothesis says nothing occurs, or in line with what we've been talking about, if you give students this new SAT class, it makes no difference. Nothing happens. The alternative hypothesis is always the hypothesis that, yes, the manipulation that you have done, or addition of this class, the manipulation you have done has in fact changed people or changed the average. Okay? So the null, nothing happens. The alternative, yes, that manipulation that you have created has in fact made a difference. Okay? So the first set, we're going to talk about stating these hypotheses, and I'll keep it simple here. I'm going to take an example off to the side because all of a sudden this SAT example is going to be a little weird. So as an example, perhaps I'm like, I think if I play white noise in the background while people taking an exam, it's going to affect their scores. And I don't know if it's going to improve them or make them worse. I just think it's going to affect their scores. Okay? So I believe if I add this manipulation of white noise, it will affect exam scores. But I am saying nothing about, it'll make them better, it'll make them worse. No, I'm just saying I think the addition of white noise will somehow change the exam scores. Okay? So the null hypothesis says the mu treated equals a mu untreated. What does that mean? The mu of, let's say untreated. The mu untreated equals exam scores with no white noise treated equals exam scores with white noise. And so the null hypothesis simply says if you add noise, mu treated, then the exam scores will be exactly the same if you didn't add white noise, mu untreated. Okay? Equal to each other, no difference. The alternative hypothesis is the exact opposite, right? The mu of the treated, in other words, if I add white noise, then exam scores will somehow be different if I did not add white noise. Okay? So that's basically what these two read, all right? They are either exactly the same or they are not exactly the same. It's pretty important to say that these two hypotheses have to account for every possible outcome in the world that could possibly happen. Either white noise does affect people or it does not. Okay? There is no possible thing that could happen in this study. Either it does or does not. Okay? So, powerful outcome. And so, hypotheses can be directional or non-directional. The ones I just wrote are non-directional. Okay? They don't predict anything for direction. There's like, I just have zero idea if this white noise is going to make them better or worse. I just really think it's going to somehow change your performance. Okay? However, if you have a good reason to believe about your manipulation, say for example, I created this SAT class and I truly believe, I don't believe the SAT class is going to make scores get worse, right? I think it's going to make them get better. Okay? So I have to write a directional hypothesis to reflect the fact that I'm just not saying, I don't know, something's going to happen. Instead, I'm saying, I believe I am going to change the exam scores in a positive direction. Okay? So these are going to be directional. Taking a look at what a directional hypothesis might look like. Okay? Oops, that top line should say SAT, and I swear I caught them all, but apparently I missed that one. Top line says SAT. So you've created a class that you think will improve SAT scores. Your hypotheses are going to read the mu of the treated is less than or equal to the mu of the untreated. In other words, in fact, it's easier if we understand the alternative first, because the alternative is very logical. The alternative hypothesis simply says the average SAT score treated after taking my class is greater than the average SAT score if they did not take a class, untreated. Okay? And that makes sense. I mean, this is implying that my SAT class raises scores. Now, the null hypothesis is a little counterintuitive, but remember, these two hypotheses must incorporate every possible outcome that could occur. Okay? And so the null hypothesis literally says either the mu treated is exactly the same as the untreated. In other words, if I give people an SAT class, it does not change your scores at all, or you take an SAT and it makes them worse. Okay? The reason this is because only the option if my class improves scores, that's important because I can sell my class, I can make money. If my class does not change scores, I can't sell my class. If my class decreases exam scores, both decreases and keeps them the same are garbage to me. Right? I'm trying to market my product here. So both of these outcomes, either equal to or less than, are both crap. Okay? And so that's why they're both in the null hypothesis. It does not have the effect that you want. But again, these two outcomes, or hypotheses rather, cover every possible outcome that could ever possibly occur in the world. So now we have to set up a criteria for decision. Okay? And so we're going to have to review a little bit. Okay? Remember the shape of the distribution of sample means. Okay? We got to remember this. Remember the distribution of raw scores might be normal. The distribution of sample means will always be normal. And if this is a surprise to you, go back to lecture 5 and kick in that central limit theorem again, because that's how it went. No matter what the population of raw scores looks like, the distribution of sample means will have a mu exactly equal to the mu of the raw scores. It will have a standard deviation that is going to be called standard error, and it will be equal to the original sigma divided by the square root of n. And As the size of the sample, n, goes up, the distribution of sample means will approach a normal distribution no matter what the raw score population looked like, okay? So go back, and if you don't get that, you better make sure you get a good handle on it, because that is the fundamental idea that justifies all of these inferential statistics, okay? All right, so now, I will explain that next time. So now, if I have a see, I told you I got the SATs on all the other slides. I missed that one. If I have a distribution of SAT scores, then I can create a distribution of sample means for size sample n. Okay. We must locate our sample. Okay. Let me see if I got what I have in the pictures. I made a bunch of crap in the hospital yesterday while I was waiting. So let me see. There. Okay. Here we got a population of raw scores. Oh, mu is 1060. Whoops, ignore the fact that I said mu was 1,000 earlier. I looked it up yesterday and I forgot. So the mu of SAT scores equals 1060, and the sigma is 195. These are raw scores. You see it, raw scores. And so we've seen the way we can map this out. We put 1060 at the center, and that maps out to a z-score of 0. Go up one standard deviation, so 1060 to 1255. I'm adding 195 there. And 1060 to 865, I'm subtracting 195. So we've seen this before. And so we create a distribution of sample means. And so we're going to create a sample mean of size 30. Okay? So here is the same SAT scores, but now we're going to take a sample of SAT scores and create a distribution of sample means. Number one, I don't know if my drawing does a good job, but see how spread out the raw scores are? See how clustered and tight these are, okay? Look at this. This one is centered at 1060. This one is centered at, come on, buddy, 1060. Exactly the same center, right? We know that. Take a look up in the top. You can see I've got sigma sub x bar equals sigma sub x over the square root of n. The original sigma was 195. Take a look. We're using a sample size of 30 for this example. So 195 over the square root of 30 equals 35.6. And so we see in this distribution of sample means, we can put 1060 in the center, and then 1095.6, which we 1060 plus 35.6. There's what the hell is that? 1024.4. That is 1060 minus 35.6, right? And so in the same way that I can sort of create map out on the raw score distribution, raw scores compared to z-scores, I can map out sample means compared to z-scores, right? It's the same type of a distribution. What one did I make over here? I forgot. Oh, I didn't mean to do that one. I meant to check this one. Okay, so imagine this. I am going to give my SAT class to 30 people, and when I do, I get it's behind my face, of 1150, okay? I did a sample of 30 students. 30 students took my SAT class, then they took the SAT. They scored, on average, 1150. And so here's what I'm going to ask you. Did my SAT class make a difference? Okay? The other day we started talking about, is this a freaky sample? Is this such a strange sample that I'm going to call it a weird sample? And that's part of the story. Because what we're going to do is we're going to look at this and say, do I have a reason to believe? You see this 1150 here. Do I believe that this 1150 really belongs to this distribution of sample means? Or is it more likely? You take a look there. The distribution on the left is the distribution of sample means for SAT scores, the same as the last slide. But now what I've drawn here is a hypothetical, a new curve. Is it possible that I have literally shifted the average with my class? So we see on the left is SAT scores without test, and on the right is SAT scores with test, or with class. I mean, SAT scores without class, SAT scores with class. And is it possible? So I guess the question is, what do I believe? Do I believe that this 1150 that I found, does it belong to this group right here, to this distribution? Is it a member of this distribution, or do I have evidence to believe that this 1150 actually belongs to a different sampling distribution out there? Here's the thing. If I come to a conclusion that my sample of 1150 truly belongs in this distribution here, I'm effectively saying your SAT score did nothing. Sure, this is a high average that these kids got, but it's not high enough for me to believe that you actually made a difference. If this is the conclusion that I'm going to come to, come on, if this is the conclusion I'm going to come to, what I'm saying here is basically because this 1150 belongs in this new distribution, your class really, truly made a difference. You have truly and utterly changed these scores by adding the class. Okay? And so this is what hypothesis testing is coming to. Is this sample that I've drawn a member of this distribution, in which case the class does nothing? Or is this sample a member of this new distribution, in which case, yeah, I have done something? And so these are those two hypotheses going backwards, and this is kind of the image. You've done nothing, you've done something. This is what the null hypothesis said. Sorry, buddy, you haven't done anything. The alternative hypothesis said, yes, you have. You've truly created something new. Okay? And so setting the criterion for decision. What we need to do is work with something. This is a brand new word called alpha. Now, we use it in the Fred and Ethel's bowling example, and I forget what they called it there. They had a strange little word for it that I can't remember. I guess you could look in your notes. But we're going to call it alpha from now on. And so when we had that 0.05 and we split it into two tails, effectively we were saying alpha. And we're going to talk about this word alpha in a lot of cases. Now, alpha is something that will be told to you, okay? If you ever come to the end of a problem and you're ready to calculate and alpha has not been told to you, then you better come to me and check, because it needs to have been told to you, okay? So alpha is something that gets selected. And we'll talk more at some point. One of the labs I'll describe this alpha and why we would choose one versus another. But in psychology, 0.05 is a fairly common alpha, or maybe 0.01 are quite common ones to use. But you will be told alpha. Okay, it will be stated for you. Okay, and so what we find is, where is it? Alpha will determine where our regions of rejection are going to occur. And again, in that Fred and Ethel example the other day, if you recall, we said, okay, 0.025 to the left, 0.025% to the left, 0.025, or 2.5% rather, 2.5% to the left, 2.5% to the right, if you recall that. And so it creates the region of rejection. We'll get some more images here. Where are you? Okay. So what happens is we need to figure out z-scores that create a region of rejection. Okay? So this is going to be tricky for us. I'm sorry, this is your least favorite part. But this is where we're going to have to go to the z-score tables and find probabilities and figure out what z-scores match up with them. Okay? So let me see. There's a lot of words here, but I actually put together some images for you. In fact, let me show this image first. Okay, check this out. In this image, you see I've got a distribution of z-scores, okay? And let's say you were told in this problem, alpha equals 0.05, and this is a one-tailed test. What it's saying is you need to figure out the z-score that separates the top 5% of the distribution, okay? Now, we know how that silly z-score chart works, and we want that 5%, but we know we will never find that 5%. Because, of course, in the z-score distribution, all you get is the distance between the score and the mean. And so if 5% fall to the right, then 45% fall between the z-score and the mean. And so let's check this out in this image right here. Oh my goodness, I need glasses, tiny little words. So we need to find a 0.45. Oh God, I wrote it on the other screen. So now you need to find a 0.45. Oh, tiny, 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 tiny. Oh, I hope Jenna's wearing her glasses. Oh, 0.45, 0.4501. I got it. 1.65 is 0.450 something there. So point. So lo and behold, a z-score of 1.65 separates the top 5% from the rest of the distribution. Okay? Similarly, I could go alpha equals 0.01, one tail. Okay? Oh my God. Again, I want the 0.01. I'm not going to find the 0.01. Instead, I'm going to find 0.49, right? The 49% between that score and 0. And so we'll go to the chart, and now we need to find 0.49. Oh my goodness, 0.49. Oh, 0.496. Oh, I see where. 4871, 48. What the heck? 0.489, 0.4893, 4896980. What is that? 2.33, 2.33. Good, that was hard for me to do. So look at that. A z-score of 2.33 separates the top 1%. Huh? Simple dimple. How about if we were doing some two-tailed stuff? Okay, so if we were using non-directional if we were using directional, these are directional hypotheses. I have a reason to believe that the class improves scores. But if we were using non-directional tests, okay, then we would take our alpha levels, and here, for example, nope, wrong one. Here it is. Okay, so if I had alpha equals 0.05, two tails, what it does is it takes the 0.05 and it splits it into two parts. Okay, so that 2.5% are on to the left, 2.5% to the right. Now this is exactly the number we looked up in Fred and Ethel's bowling alley. But again, we'll never find the 2.5% in that chart. Instead, we'll find the 0.475. So let's take a quick peek just to remind ourselves that it's true. 0.4750 is at 1.96. I remember that one is a perfect fit. Okay? And there it is. Okay? And so these are going to be my, quote, regions of rejection. Get ya? And so we find, say, for example, in this one, for example. What this says is if you, now in step 3 or 4 rather, we're going to compute the z-test. Well, it turns out if the z-test is less than, given this that you're looking at in front of you, this indicates that 1.65 sets up the region, what's called the region of rejection. Everything above 1.65 will be in the region of rejection. Everything to the left of 1.65 is in the region of non-rejection. Okay? And so what happens here is when we calculate our z-score, or our z-test, the question is going to be, is the obtained z-score that you just calculated greater than or less than 1.65? Because if it's greater than 1.65, we're going to reject the null. I'll describe it more. If we're less than 1.65, we fail to reject the null. And so this area right here that is set off by these critical values will become very important in hypothesis testing. And so, yeah, as I said, step 3 is a joke. I mean, this is stats class. You don't have to worry about it. We just give it to you, right? Here you go. Here's some numbers, okay? And it's actually kind of difficult to do somewhat because in the real world, you gather your own numbers, okay? And so evaluating the null hypothesis, you know what? I did not even calculate this z-test. Silly me. I was doing all of this other stuff and I didn't calculate it. But we know how to do this. So you guys grab your paper and pencil and pen and pencil and pen, and we will talk out the steps for you because I don't have a calculator. I'm just winging it on the spot. So going back to our example. That's right. The mu was 1060 with a sigma of 195. Okay. We have already calculated the standard error of the mean is 35.6. Okay. So we have the numbers necessary. And so coming down back to where we were, 35.6, 35.6. Okay. You need to create z equals sample mean minus mu over standard error. Okay, that is, our sample mean is 1150. Our sample mean is 1150, so it's 1150 minus 1060 divided by 35.6, the standard error. Now, what is that? That's 90 over 35.6. And so we would need to figure out that number. 2.7, I don't know, I'm coming up with it. And check this out. If I calculated a 2.7, there we go. Look at this. Is the value of 2.7 that I just obtained in the region of rejection? Okay, it's not 2.7. You guys do the math on it. I estimated it, right? Is the value that you just calculated for that z-test, is it larger than 1.65? And the answer better be yes, okay? It better be. And so we'll come to a conclusion here, reject the null hypothesis, okay? So now, for today, I'm going to stop there. And I know this is kind of a crazy, creepy, crappy stuff, okay? Feel free to watch this one a lot because we will definitely do hypothesis testing over and over and over. The details will change, the idea will not, okay? So now for Thursday, I might make it to class. I don't know. Either way, if I make it to class or don't make it to class, we will be going over some great examples of how to do this z-test, okay? So all we're going to do is just practice on Thursday's stuff, okay? And again, it could be in class, it could be on the computer. I don't know. It depends on how I'm feeling, okay? So check this one out. Make sure you get it, and we'll see you later.